So as the title suggests, I'll be talking about change attribution and trends in delta outflow and salinity over about the last, roughly the last century. And what I'll be doing, I'll be summarizing some work that my colleagues and I have been working on for a few years. In fact, if you were here in the last session, John Rath gave a talk on some ANN modeling, and that was part of a linked set of work that was being done to get at this issue of trends and change attribution. So, so why? Kind of the question: why are we interested in this? For those of you involved in the Central Valley Bay Delta issues, there's a lot of activity going on with respect to ecosystem restoration and flow regulation. So, I believe that to make informed decisions on those, one thing we need to know, well, what were the antecedent conditions? What did things used to look like? And to the degree we would know why have things changed? So that's what kind of this work is looking at. So over the last 9 decades, there have been a lot of changes, a lot of anthropogenic changes, as you see in the slide. Reservoir construction, a lot of increase in irrigated acreage in the Central Valley, and certainly population growth in the south, leading to more exports of water from the delta. And so what I'm going to do now on this slide, again, it's going to be just picking a few highlights. I'm going to go over what I think are 4 key findings from the work. I'll talk a little bit about the methods and show a few of the results as well. And for those of you that might want to drill down into this a little bit more, there are 4 papers that have been published on this subject. And again, John Rath talked about one of these in the last session on the ANN implementation. And you can either, these are freely available. You can either come and talk to me after the session or sometime later, or if you want to wait till all these presentations get put up on CWEMF's website, there is a bibliography at the end, and you can see the citations there. And then before I move on, I just want to make some acknowledgments. This work, this series of work, was funded by the Metropolitan Water District, state water contractors, and Delta Mendota Water Authority. And then again, this work was really a team effort, and I'm acknowledging here the Tetra Tech team. So John's here, and Sujoy was moderating the last session. And then also Andy Draper, he's not here this year, but with Stantec, he assisted in some of the work as well. So so now I'm going to move on. I'll start talking about the trend analysis first, and then I'll end and talk about more of the change attribution. So this slide just gives a little kind of some highlights of the methods. So with the data, we looked at monthly average data and looked over roughly a 9-decade period starting in the early 20s. Statistical tests to look at significance of trends. We used Sen's non-parametric test of slope, and we used the Mann-Kendall test to determine statistical significance. So Mann-Kendall is good in that it is a hypothesis test, so it can tell you about statistical significance, but it does only apply to monotonic trends. So some of the trends are more complex. So we also looked at a seasonal trend decomposition, where you could look at a non-monotonic trend, but it's not a hypothesis test, so it doesn't tell you about the significance of the trend. Lastly, so in this work, we looked at several different flows, several different types of salinity, but for the main focus, and certainly the focus of this talk, is looking at delta outflow and X2, which which is a metric of salinity in the delta. So there's a lot of information on this graph. So this is the first significant finding. So seasonally, there are some statistically significant trends that have taken place over the last 90 years. And there's a lot of information on this slide. I'm going to direct you just to that top row, which is delta outflow. And to orient you a little bit, the left-hand side, that's the entire 9-decade period. And thanks, we'll go old school today. I feel like Hubert at Colorado. The left is the 9 decades. The middle box is the first half of the record, and then on the right-hand side, that's the latter half of the record. So I think the things to point out for the full period, the blue bars indicate statistically significant trends, and the gray bars are non-significant trends. And so what you'll see for the full period of record, there are 6 months where there were statistically significant trends, 4 decreasing. So that was November, February, April, and May, so winter, spring months. And then 2 months where over the 9 decades actually flows have increased, and that was in July and August, so in the summer. I'm going to conclude from this slide and just point out that just visually you can see, okay, those were the trends over the 9 decades, but if you look at the early part of the record versus the latter part of the record, there's a big difference. Things really changed quite a bit between the early part of the record and the latter part of the record. So that kind of draws me to when I go over kind of the broad conclusions is that when you want to think about what's going on here in the Bay Delta, you really want to look at as much of the record as you can. You don't want to focus on one period of the record because it'll give you a bias and considering what's happened. Okay, now this is those are seasonal trends. Now this is the annual trends. Oh, you have a pointer. Thank you. Thanks, Hubert. So again, a lot of information on this slide. This time I'm just going to have you look at the left-hand column. So and specifically the delta outflow. Really, the quick answer here is kind of for some of you that maybe haven't been looking at the data a lot, it might be surprising. There isn't, over the 9-decade period, there isn't a statistically significant trend in delta outflow on an annual basis. Now, I think a lot of the explanation for that is that the hydrologic variability in the system is huge. So I think a lot of these statistical trends can get hidden in that high variability. But what you see here is over the full period of record, there is a nominal decreasing trend in outflow, which would make sense because we know that water development has taken place over the 9 decades. In the early part of the record, there was a nominal increase in the delta outflow, and then in the latter part of the record, a nominal decrease in the outflow. So now, still staying with the annual trend, but to look at it a little differently, since I mentioned this kind of this high interannual variability, what we're doing here is we're normalizing the flows to kind of the hydrologic conditions, and I use the 8-river index as the normalizing factor. So in this top graph, this is delta outflow, and this is a normalized delta outflow. And I broke the data set into 2 groups, a wetter period, which are the black dots, and then a drier period, which are the red dots. So I thought this was a really interesting slide because in the wetter years, you could see over time a decreasing outflow over the 9 decades. But in the drier years, you can see once you got to about the 1980s, that trend really has flattened out and stopped. So in terms of a normalized outflow, we're not seeing lower outflows. And I think the simple explanation for that is that that's right around the 80s is when the state board regulations came in place, D1485, D1641. So we're really putting a floor on the minimum outflows that are going on, and that would have regulating outflow. So that's really put a floor on the delta outflow. And to kind of to validate that that explanation, here's a graph on delta exports. And when you look at it, first I have to tell you, you're going to be confused by the sign convention. We had to kind of bow to the reviewers. They wanted a different sign convention. So when you see delta exports going down, it actually means, think of it, the delta exports are actually going up. They just wanted it to be consistent with these trends. So in wet years, you've seen there's been a continued trend in wet years, an increasing delta exports in wet years. But look at what has happened in the drier years. Not only back in the 80s, on a normalized basis, the exports have actually been decreasing, again, in response to meeting flow regulations. So the next finding, so far we've been talking about flow, now we're going to salinity and X2. And so really the finding, which again is not too surprising, is the salinity records are supporting what the trends that we were seeing in the delta outflow record. And I'm going to just point out two interesting things here. So for orientation on the y-axis, we're looking at X2 position. So higher numbers mean saltier, lower numbers mean fresher. And we're looking at the water year type going from critical all the way to wet. So the interesting thing, if you look at the critical year, and then the red line and the red dots indicate the early part of the record. The blue lines, blue dots are the latter part of the record. So I think the interesting thing to look at over here is the more recent period of record, the seasonal variability has been dampened through project operations. So the early part of the record, it used to be a lot saltier in the summer and early fall, used to be a lot fresher in the spring, and now the project operations have dampened it. It's saltier in the winter, spring, and it's fresher in the summer, early fall. Now contrast that with wet years. They're really, kind of visually, you'd say there's not a whole lot of difference. And again, when you think about it, the system in the wet years, it's the projects really have much less influence on what's going on. It's more hydrology driven. So the projects and the land and all the other water management really have less influence on what's going on in wet years. Okay, so I'm going to move now from the trend analysis to the change attribution analysis. So why are we seeing the changes that we're doing that we're seeing? And this gets into a little bit more modeling to ask that question. And so we used kind of some superposition principles to come up with some scenarios to look at change attribution. And then we defined a 1920 level of development, which this map is showing kind of irrigated acreage in 1920 versus a more of a contemporary condition. And just what I'll say is when we develop these scenarios, we use the 1920 level as a baseline for change. And then to develop the 1920 scenario, we removed or unimpaired the project operations and some of the reservoir operations from the larger non-project reservoirs. And I'm going to have to move along here. This is just a definition of some of the scenarios. So we defined 5 different scenarios, which basically there was a 1920 level and there were some unimpairments of the historical record. And then to get to this issue of change attribution, it really ends up being kind of a difference, looking at the differences between one scenario and another. So for example, the total change would be the difference between the historical scenario and the 1920 level. I'm not going to say much about this. John talked about this. We used the model that John talked about in the previous scenario, which is a salinity as a function of delta outflow and tidal conditions. And John actually showed a chart like this. there's a lot of information here. I'm going to so this is really finding number 4. It's really attributing change to different drivers. And in the top, so orientation, right now we're talking about summer, early fall. On the top row, this is just the time series of outflow in X2. And then down here is the change attribution based on these scenarios. And here's the kind of the legend. The red lines, that's the total change based on the 1920 level. The blue line is the projects. That's a CVP, SWP. You've got non-project storage in green, non-project diversions in purple. So you can see, as we talked about before, the total change, it was increasing flow in the summer, decreasing salinity. And so the quick kind of one thing to look at, the projects through their operation are really supporting that higher flow, and it's more than mitigating for the kind of the decreasing flows that are accounted for by the non-project diversions. And then you can see it's kind of the mirror image here with the salinity. This is the same graph, except now we're talking about spring, April, May. And I mentioned all the drivers are resulting in lower flows in the spring and higher salinity. And here, if you look at it, you'd say you'd attribute roughly half and half between the project operations and the upstream non-project diversions are contributing to the spring flow changes. I'm going to skip this one, and I'm going to move to my concluding thoughts. So again, what was the motivation? Understanding how and why flow and salinity have changed over time will inform ongoing deliberations on watershed and estuary management. Again, looking at the early conditions versus the late, biological inferences based on a truncated subset of the data are not representative of trends associated with the full hydrologic period. The third I didn't really get into, but it's kind of would be a corollary, would be even this full hydrologic record isn't indicative of the natural or pre-development conditions, because there have been well-documented alterations that had already occurred by the 1920s. And then lastly, you can use modeling tools like this to attribute the attribution of change to multiple drivers. And that concludes my talk.